All right. So, like I said, the topic that we are going to be talking about today is sound wave, and that topic is an interesting topic, just like every other topic. Like I always say, physics as a subject is not difficult. The major thing is just for you to understand the concept. Then you must have a very good background in mathematics. The moment you have a good background in mathematics and you understand the concept, you are good to go. So when we talk about sound wave, the part of the objective that we'll be looking at is that we should be able to define sound wave with its characteristics, with its features. What are those things that we'll see that will make us know that yes, this is sound wave, and we will be able to talk about the properties. See, those three things I just mentioned now, they are different. There are three different things. When you talk about features, characteristics, properties, right? They are different. Then we talk about the speed of sound. Now, when you talk about the speed of sound, it varies from medium to medium, as we'll understand later how sound wave works. So that is one of those things that we'll talk about. Then later we'll talk about one of the effects, or the observable effect of sound, which is music and noise. So we'll try to look at the difference between the two of them. And after understanding the difference between the two of them, we'll quickly talk about the beat and its frequency, talk about the characteristics of sound wave, and if we have the time, we'll go into echo and its application. So by the time we are done with that, we'll now go to another topic under sound wave, but it's another subtopic that we call resonance. That's where we have most of the calculations. But for now, let's start with sound wave. So I'm going to send the slide now so that we can follow what we have there. So um, because of time, permit me just to go straight by explaining one or two things from the slide. But like I always say, I would prefer, and it will be appreciable if you can also contribute. Whenever I'm asking any question, you quickly respond by putting it on the chat page, and I'll be able to identify whether you are with me, or you are still having one or two challenges with your response. So sound wave. So like I said, the objective of this class are: number one, we should be able to explain the features of sound wave as a longitudinal wave and mechanical wave, explain the variation in the speed of sound in different media, explain the effect of temperature and pressure on the speed of sound, distinguish between noise and music, explain the characteristics of sound wave and the factors they depend on, define echo and its application, and highlight part of hearing aid. I will not dwell much into that hearing aid. All right. So now, before I even go to the next slide, can someone remind me? Okay, because we don't want to waste time, let me just quickly go straight and tell us the definition of wave. I am sure some of us, we have been taught wave by the second instructor. I am very sure that she has explained it. I saw it on the scheme that we have with us. So if you look at wave, um, we said wave is a disturbance that transmits energy from one point to another, or transfers energy from one point to another without causing any permanent displacement of the medium itself. I'm sure you still remember that that is the definition of wave. Now, when you talk about that wave, there are two major concepts, or um, two major phenomena there that you need to understand. The moment you understand those two things, that is what revolves around everything called wave, and that is what the particle and the medium. The medium is the space where that wave is transmitted, even not only transmitted, where it is produced from, right? Then when you talk about particle, the particle is what is carrying that wave energy. What is carrying the wave energy is the particle, while the medium is just the place, the region, the space where that energy is being transmitted, right? So if you remember that definition, yes, you will see that that definition gave a clarification that we have different types of waves. If you remember, types of wave based on that material medium, not the particle now, the material medium, the medium where that wave will be propagated. So we all know that we have mechanical wave and electromagnetic wave, right? Um, Mechanical wave is that wave that requires material medium. We know the examples like water wave, like sound wave, like wave from a plucked string, and some other examples. While while the other one, which is the electromagnetic wave, is that type of wave in which there is no material medium for its propagation. It does not require material medium for its propagation. So if it does not require material medium for its propagation, the only kind of space that we can have for such medium that is not a material medium is a vacuum. A vacuum is a space or a region where there is no matter in it, right? So when you talk about the one that have matter, we are talking about the solid, we are talking about the liquid, we are talking about the gaseous. In fact, to a higher level, they can say we are talking about the ionized region. Ionized region is more like a gaseous region in which the molecules of the gases are ionized, right? So talk about the other one, which is the electromagnetic wave. It does not require material medium. So it is just a vacuum, it's just in space. And that is the one that we acronym as revoxim, radio wave, infrared, visible, ultraviolet, X-ray, gamma ray, and the microwave. So that is the one talking about electromagnetic. All this we are doing is revision. If not that I'm trying to conserve my time, I would have asked you to define all these things. But I'm sure that if I ask you to do that, you may not give me the response on time. So I'm sorry, I'm just quickly doing this, right? So the second one is when we talk about the types of wave, there's another types of wave that we have talking about the particle, talking about the particle and the medium. In what direction are they? Are they in the same direction? Are they moving in the same direction, or they are moving in opposite direction, or they are moving perpendicularly? Take note that when the wave, when the medium and the particle are moving in the same direction or opposite direction, but on the same plane, that means they are parallel. They are on the same plane, they are on the same axis. It could be that they are moving together. It could be that they are moving in opposite direction. That is when we call the wave longitudinal wave. But when the direction of the particle and the direction of the medium are perpendicular, perpendicular means the angle between the two of them is 90 degrees, we say that that is a what? A transverse wave. Now, talking about the sound wave that we want to explain now, sound wave is a mechanical wave and is also a longitudinal wave, right? So you should take note of that. A sound wave is mechanical and longitudinal wave. So that is what I just said here, that when you talk about the definition of sound, you must first understand that sound is a form of energy. And that's why when you are defining wave, I think it is fair, as far as I'm concerned, that you should be able to tell us that it is a disturbance that transmits or transfer energy, because that energy is what makes us to call it different types of wave, like this, the sound wave, the water wave, even there is the wind wave. Yes, there's wind wave, right? All those kind of wave, there it will have been that a form of energy is being transmitted, right? So when we talk about sound, is a form of energy produced by a vibrating body. So it is only a vibrating body that produces sound wave. If a body is not vibrating, if the molecules are not vibrating, it will not produce any kind of sound. So we said that sound wave is a mechanical wave, as I've explained earlier, and it's a longitudinal wave. You need to take note of this. It's a common objective question. Even in theory, they will ask you to distinguish between sound wave and they can say between sound wave and radio wave. So you know sound wave is mechanical and longitudinal, but radio wave is electromagnetic, and it is also transverse. So that's the difference. Now, one of the features, I said the other time that we should understand the difference between features and characteristics, right? So one of the features of sound wave that we need to know is that, having said that sound wave is a longitudinal wave, every longitudinal wave is characterized by compression and rarefaction. So you can see that in that picture, that diagram that is at the right side of that definition. It is characterized by compression and rarefaction. So compression is those region where the air pressure is high. So we have high pressure there. But when we talk about rarefaction, it is low. So there is gap. There is gap. And if you have been to the studio, or you listen to like a karaoke on how music is being played on those old DVD player and some other things, you will see all these things when you have all this spike up and down. So the point where you have the highest spike is more like the place that you have the high pressure. That's like the compression. And the one with low one is the one we talk about, the rarefaction. The same application is in the way our heart beats. Right? You look at the heartbeat, beat, 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 beat. If it is observed on a kind of oscilloscope or something like that, you see how it oscillates up and down. So that oscillation is more like a vibration, and vibration is what makes a sound to be produced. And that's why you hear, if you put your ear close to your heart, you hear the heart beat stronger. But as you are moving away, you will not hear it very well. And that's one of those things I will be talking about later. Then the next thing on the slide is to talk about another definition of sound. That definition makes us understand something about the variation of speed of sound. We have just defined sound, and we have just said that sound is a form of energy. So if something is transmitted from one point to another, it will definitely have speed with which it will move from one point to another. If you remember your wave, we said that there's what we call wave front and there's what we call wave form. Wave form is the pattern of that wave as it is being transmitted. But wave fronts are those points on those wave form where the energy is being transmitted. So for it to move from one point to another, the time it takes to move from one point to another, when you find the ratio, it would tell us the velocity or the speed of that sound. So the speed is the speed of sound in solid. If not for time, if I had asked, I am very sure some of us would believe that the speed of sound in air is faster than other ones. But with the example I just gave now, our heartbeat, you can hear the heartbeat when you put your ear closer to the chest of the person that you want to hear his or her heartbeat, right? So if you are moving farther away, right, there is a gaseous gap between that body and yourself. So because of that gaseous gap, you will not hear that heartbeat again, or probably very well. But as you put your ear closer to the heart, you hear that sound. So I said sound is the vibration of kinetic energy passed from molecules to molecule. So because the kinetic energy, if you remember the explanation of the kinetic theory of matter, that will even make you understand better why we say that sound is transmitted faster in solid than in liquid, right? So because when you talk about the kinetic theory of matter, one of those things that it makes us understand is that the molecules are vibrating about mean position, and we have just said that vibration is what produces sound, right? So the closer the molecules are to each other and the tighter they are bond, the less time it takes for them to pass the sound to each other, and the faster the sound travels. So speed of sound is fastest in solid, followed by liquid, followed by gas, right? I hope that is clear. If anything that I'm explaining is not clear to you, kindly respond on the chat page so that I can reiterate it again. Then, with what I've just said now, I've just told us the features of a sound wave, right? I've told us the features of sound wave. I've also mentioned that sound wave we are talking about it has speed, and that speed varies for different media, right? Then we are now going to the properties that affect that speed of sound or velocity of sound, as the case may be. Now, there are some things that affect the velocity of sound, while there are some things that do not affect. But generally, we have what we call the temperature, the pressure, the elastic property, and the density. These are the four properties that affect the speed of sound or the velocity of sound. However, pressure is not going to affect the speed of sound in gas, in solid, in liquid, and even in air. It may be affected variably, just a little effect for that air. But in gas, it is independent of it, it does not affect it. But when you talk about temperature, temperature is always affected. Now, I need to make a correction here that I saw a question where they were talking about the speed of sound in air is directly proportional to the square root of temperature. Now, that statement, I'm still trying to clarify that statement, but as far as I'm concerned with the research I have made, the only relation that we have between the speed of sound and the temperature is this formula that I give, that is given there. That is the formula which shows a partial variation. If you remember your mathematics very well, you see that V is partly constant and partly varies directly with temperature. That is what that formula depicts. If you remember your variation very well, right? So it is not square root. I now think that I stand to be corrected, but what I think they are trying to say is that for A-level physics, there is an aspect when we talk about thermal physics, talking about the vibration of molecules, that we were taught, which is a basic concept, that the average kinetic energy of molecules in a particular medium, in a matter, the average kinetic energy is directly proportional to the absolute temperature, right? If that is the case, then the average kinetic energy is actually given for a monoatomic gas. It's an A-level thing. You don't need to stress yourself, but it's good if you can make that research. For monoatomic gas is actually 1/2 kT average kinetic energy. For diatomic, it keeps on going like that. KT. For polyatomic, we have 3/2 and so on. So if I look at that average kinetic energy, if I am to bring out velocity from that average kinetic energy, you will agree with me that kinetic energy is half mv squared. So if we are ignoring the mass of that molecule, right, you will see that the v squared is directly proportional to the temperature from the formula I've just said now, that half kT for monoatomic. So if V is equals to half, if half mv squared is equals to half kT, right? Then V squared is proportional to T. That means V is proportional to the square root of T. But that speed that we have there is talking about the speed of the molecule in that matter, not the speed of the sound. So that's why I personally feel that statement, I've seen it in WAEC question before, and they gave the option of directly proportional to the absolute temperature, inversely proportional to the absolute temperature, directly proportional to the square root of the absolute temperature, and directly proportional to the square root of the temperature. They didn't say absolute. So I feel, I stand to be corrected, but I feel that the right thing should be that the velocity is directly proportional to the temperature by partial variation. So that is that. So you need to take note of that formula. All right. So taking note of that, let's move on. Let's move on. So the last thing I said, I've explained temperature, then I've just told us that pressure is independent. Then we'll go to the elastic property. So for solid, the elastic property is Young modulus, which shows that velocity is directly proportional to the square root of the Young modulus. For fluid, when I say fluid, I'm talking about liquid and gas. It is also directly proportional to a factor that we call bulk modulus. Then it is inversely proportional to the molecular mass, inversely proportional to the square root of the molecular mass for air, right? So we have that. Then density, the velocity, the speed of sound or velocity of sound is inversely proportional to the square root of the density. These concepts, they are important because they often ask the question in objective. They usually ask it, so it's important to understand that, right? Going to the next slide, I gave an example there. So I think that example is straightforward and very clear. Just look at it. Based on the concept I said the other time that the speed, the velocity is inversely proportional to the square root of the bulk modulus. So that is what I've just used. I mean, directly proportional to the square root of the bulk modulus. So that's what we have just done there. So if the bulk modulus in a fluid is doubled and the speed of sound was initially 300 meters per second, so what will be the new speed? So we have that. So I will move on. If there is anything that is not clear to us, if there is anything that is not clear to us, you can quickly notify. Mr. Fabian, this is not a TSS3 class, so it's only for SS2, SS class, please. So we have the initial speed to be 300 meters per second. The initial bulk modulus, you identify it as an alphabet. I prefer B, while the new bulk modulus will be twice the B because they say it's doubled. So if that is the case, you find the new velocity and you have that mathematical evaluation. So it's clear, I guess. So if there's anything that is not clear to you, you can raise your hand and let us know how to explain better. So I'm taking this little few seconds so that you can look at what I've solved. If you want to write it down, you can quickly do that so that I'll move to the next slide. All right. So if you understand this one, the next slide follows the same principle. So I'll not even take my time on that. Just like 5 seconds, look at the question and I'll move on. That's why I'm taking my time on this. It's very clear, right? Moving to the next slide, you have another one, a question on Young modulus. It says a source, a sound source produces sound moving at a speed of 20 meters per second, enters an elastic block of Young modulus that's 2.5 Newton per meter squared. If the same sound wave enters another block of Young modulus 10 Newton per meter squared, what will be the new speed? So you are talking about a particular material with its own Young modulus, but it's the same sound source, right? So by the time it enters through that material, but if you change that material to another thing, it will not have the same sound, obviously. So that is what we have just explained there. Now, talking about the properties of sound wave, I think this time around, I would need some of us to respond. Can you remind me, can you tell me the properties of sound wave? I need some of us to tell us the properties of sound wave. Taking note that sound wave is a longitudinal wave. If you remember what you have been taught in wave, there are properties for longitudinal wave and there are properties for transverse wave. So the properties of longitudinal wave are the properties of sound wave. So I need you to respond this time around, please. Yes, you can unmute yourself and respond, or you type it on the chat page, please, quickly. I'm still waiting. Okay. Okay. I would like to know if all of us actually can hear me. Because someone said she has not been hearing anything since. Okay. Someone said loudness. No, no, that's not the property of sound wave. Yeah, that one is characteristics. So we still get there. But we are talking about properties. Just um just imagine that we are treating wave as a topic. And I'm now asking you to mention the properties of wave. Don't let me even say longitudinal wave now. What are the properties of wave? There are actually 5 of them. Can anybody tell me the properties of wave? I'm evaluating your previous class, so I would be glad if you can get it right. I'm sure some of you will just quickly go to your textbook and try to get the answer. No problem, but I just want response. Please try. Amplitude, no. I really appreciate that you are trying. Others are not responding, but all that you have said is not yet correct. So I need 1 or 2 more persons because of time, please. Quality or tone, frequency, no. Wow. All right, let's take that correction. But I would be glad if you won't forget this again. I expect that your teacher should have taught you that there are actually 5 properties of waves. We have reflection, we have refraction, we have diffraction, we have interference, and we have polarization. These are the 5 properties of wave. I've not specified which type of wave now. All waves generally, they can either be reflected, they can also be refracted, some can be diffracted, some undergo interference, whether the interference is constructive or destructive, and some can actually be polarized. Now, for our general knowledge, longitudinal wave can be reflected, it can be refracted, it can be diffracted, and it can undergo interference, but it cannot be polarized. The reason why it cannot be polarized is because for a longitudinal wave, as we have said, the direction of the medium and the direction of the particle in this concept of sound wave, the particle will be the air molecule. The medium is also the air, right? The dust particle or the particles of the air is what is carrying the sound wave, while the medium through which that wave is transmitted is also air. That is why in space, astronauts, if they make any mistake of removing that their shield or that their helmet that they use to communicate, if they remove it, let's assume nothing will happen to them, though we know something will happen because there is no air in space, it's vacuum in space. So let's assume nothing will happen to them and they remove that helmet and they are communicating to each other. If someone is talking here, the other person will not hear, because what is carrying that sound wave is the what? Is the air particle, right? So that is why a longitudinal wave, which an example is sound wave, cannot be polarized, because the only thing that can be polarized is when you have a particular the medium in one direction and the particle in another direction. So to polarize it, you will now make all of them to be moving in one plane. So, but because a sound wave is already in one plane, there is no need for us to say it can undergo polarization. That is that. So take note again: reflection, refraction, diffraction, and interference. That is for longitudinal wave, which is an example of sound wave. So these are the properties of sound wave. Do not forget, please. So it is only for transverse wave that they can reflect, refract, diffract, interfere, and they can also be polarized. So let me quickly, because of time, I'm sure if I don't explain this, you may not be able to have the idea how those properties are applicable in sound waves. So let me quickly explain, since it seems you have forgotten. Reflection is ability for a wave to bounce back after hitting a surface. So when you send a wave in a particular direction and it gets to a barrier or it gets to a hard surface and it bounces back and it comes back to you, that is what we call reflection, right? And an example of reflection in sound is echo. If you are somewhere, you are at a particular distance to what? To a particular wall or brick or anything like an obstacle, and you speak, you transmit your sound from your mouth. When you transmit it, after a while, you hear that same sound again, right? After some seconds, that is what we call reflection, right? We have other forms of other examples of reflection that you can see. Some of us usually see it when we are playing around in our area, but we don't really count it. If you have ever been to a lagoon front, like the one we have in Unilag, you see the wave, the water wave coming continuously. But when it gets to that last point, that block where we usually stand to look at the third mainland bridge at the other side, you see that as it gets to that side, it forms another wave going in the other side. That is reflection. It hits that surface and it bounces back, forming another wave form or wave pattern to the other side. Refraction, that one is talking about two media. So when a wave moves from one medium to another medium of different density, it's like something is moving from air to water or from water to glass, right? By the time that wave is being transmitted, the speed with which that wave is moving in the first medium that has lesser density. Having known what we said the other time, that the speed of sound in different media differ. So you can now imagine that something wants to move from solid to liquid. The wave wants to move from solid to liquid. We know that in that solid, the speed with which it will pass through that solid will be faster. But as it gets to the liquid, it will be slower. So because of that speed that is reducing, the direction will change. So what is refraction? Refraction is the ability of a wave to change direction and even speed when it moves from one medium to another one. So that happens with sound wave, right? Some of us may not know that it happens, but it really happens, right? If someone is in one room and they are talking, the whole room is covered. If you put your ear closer to the wall and you calm yourself, if you are calm and you listen, you will still hear some of those sound waves being transmitted. That is what Yoruba would say, "Ògiri létí," that walls have ears. So when you are speaking from one side of a particular medium, it is transmitted to the other side by the process of what we call refraction. And it is that same process that makes us to observe that in the, let me ask that question, quickly respond to that. Please, I know we are exhausting our time, but I need to explain this. Most of sound wave questions usually come out in objective as an oral question, written question, no much of calculation until we get to resonance. So I need to be sure that you understand what I'm saying. Now, when you talk about sound being transmitted during the day and in the night, which of them do you think is faster, that you hear fastest during the day and in the night? Can anybody respond to that question? When do you think speed of sound is fastest? Anybody? In the night, yes, thank you very much. That is true. And you know why it happens so? In the day, the molecules will have gained more kinetic energy. So when they gain more kinetic energy, they will be so the space between them will be much. You know, the medium, the atmosphere is normally gaseous. Yes, we know that. But there are some times that we have the neutral atmosphere and the ionized atmosphere. So during the day, when the sun is shining, that we have what we call photoionization. When there's ionization, the molecules are very, very much spaced from each other because they have released an electron have been ejected from their surface by photon from the sun. So at that time, the molecule, when you now transmit wave, when you transmit sound wave from where you are to another place, it will take long for you to get to that other side. But when it is in the night, everything is cool, right? So based on that concept of refraction, the environment is denser, at that time. So more like a solid. I don't know if that is realistic, but let me just say more like a solid gas. So at that situation, the sound wave will transmit or will flow faster, right? Then we talk about diffraction. So diffraction is when sound wave is able to pass through a small opening. Right? The explanation I made the other time, I made a slight mistake. The explanation I made about the walls having ears, that walls having ears is actually the concept of diffraction, not refraction. I'm sorry. So the concept of refraction is when you say that sound is heard faster at night than at day. But the one of diffraction is when you say that someone is speaking in one side of a room and has a wall of brick or even wood as a barrier, and you put your ear and you can hear. That means that sound has passed through the small holes, the invisible holes of those matter. Maybe it's the brick or something. As you're looking at those brick, they still have tiny, tiny, extremely small, tiny holes where wave can also be transmitted, depending on how thick they have made that material. Then interference, we all know interference. When you talk about interference between music and noise, you can distinguish how the wave is appreciated. I'm sure all of us know that you will appreciate music than noise. When people are making noise, you have many frequencies. The frequencies are irregular, it's disturbing. So you have this one falling on each other and they are not producing. And that's why when we talk about interference, we have the constructive interference and we have the destructive interference. Constructive is the one that it will give you a pleasant sound. Destructive, when everybody is saying at the end of the day, you will not get anything out of it. In fact, in calculation, we say destructive interference when we find the total displacement is 0, because they are out of phase, so they will cancel themselves out. That is destructive interference. So that is just what I've just shown on this next slide, that what causes echo, it is reflection. Why do you hear sound easier at night than at day? It is refraction. Why can you hear someone speaking in the other room without seeing them? That is diffraction. And why is music pleasant while noise isn't? That is just explaining interference as one of the properties of sound wave. So that's just the noise and music I explained the other time is what I have here now. So you should be able to define that noise is an unpleasant sound produced due to the vibrations of irregular frequency. So the sound of a horn of a car, from the horn of a car, let's say you have 2, 3, or just you can see that sound. It's so deafening to the ear. It's not pleasant. Yeah, at the bus stop or at the market, the way everybody is talking here and there all together, that kind of sound wave is what we call noise, right? Then music is a pleasant sound produced due to vibration of regular frequency. When you hear sound from the musical instrument, even if it is a drum, the way it is being hit, it will produce a pleasant sound. So that's the difference. You should be able to distinguish between noise and music. You can see that that graph or that pattern that is drawn for music. It has a definite pattern. You see, it's usually fixed. But when you talk about noise, it's just irregular, zigzag, right? So that is that. Going to the next slide, we talk about beat and beat frequency. Beat and beat frequency. Yes, someone raises a hand. Any challenge? You are free to talk, or I think it's better you write it on the chat page. You can't hear anything. Wow. Is that applicable to the rest of us? Can we hear me? Please kindly respond if you can hear me. Okay, so it means the person that did not hear, maybe it's the network from your side. Kindly adjust and work on that. All right, thank you. So on that about beat and beat frequency, beat is a periodic alteration in the loudness of a sound heard when two notes with slightly different frequencies are played simultaneously. In another way, you can define it as beats are two notes of nearly equal frequency sounded together, producing a periodic rise and fall in intensity of the sound. With all I've seen from my research, I think there is really no simple and short definition than those two, right? So just try to learn and understand the definitions so that if you are asked in an exam, you should be able to write that definition. I will repeat, beat is a periodic alteration in the loudness of a sound heard when two notes with slightly different frequencies are played simultaneously. Or you say beats are two notes of nearly equal frequency sounded together, producing a periodic rise and fall in intensity of sound. So the beat frequency is the difference between the frequencies of the two notes. Remember, we said that beat is formed when you have two notes of almost the same frequency, but it still differ. But that difference is very, very small. So when they are played simultaneously, the alteration that is produced is what we call beat. So which means we can find the beat frequency. So the beat frequency is the difference between the frequencies of the two notes, right? So we have an example there. So that example, it says a sonometer has a frequency of 259 hertz. It is sounded alongside a tuning fork of frequency 256. Calculate the beat frequency. That's WAEC 2008. So it's straightforward. You just pick one as the frequency of the first one. Just make sure it's always the bigger frequency. Anytime you are given a question and you're asked to find the beat frequency, just take the bigger frequency as F2 and take the smaller frequency as F1 and you subtract. It's as simple as that. So I don't think we should have any problem with that. Going to the next slide, we talk about the characteristics of sound. The characteristics of sound. Remember I said the other time that there is what we call the features. Features means what are those things that you will see that will make you know that this is sound wave. And that is talking about what? Compression and rarefaction. But when we talk about the properties of sound, we have talked about it as reflection, refraction, diffraction, interference, right? Now we are talking about the characteristics of sound. Sometimes the question will call it characteristics of musical notes. So whichever way they bring it, they usually alternate that statement. You should know it's still the same thing. Characteristics of sound or characteristics of musical notes. So it's the same thing. And there are three of them, as you have seen. We have the pitch, we have the quality, sometimes they call it timbre, sometimes they call it tone, right? And we have the loudness, sometimes they call it intensity. Do not mix them with each other. Don't mix one for the other. They are different. I mean, pitch is different from quality, it's different from loudness. But anytime they want to talk about loudness, they can change it. They can call it intensity. It's the same thing. Anytime they talk about quality, they can call it tone or timbre. It's still the same thing. Now, pitch depends on frequency. And you can see the definition of frequency as I've said there. That frequency is the number of cycles made by the sound in 1 second. Number of cycles made by the sound in 1 seconds. Now, I would like to ask you this question. I want to see who will get it right. Please, can you tell me the first graph that we have there, the one at the top, the one at the top, can anybody tell me what is the frequency there? What is the frequency? Having known that we said frequency is number of cycles. So what is the frequency of that first graph? And what is the frequency of the second graph? Please. I'm still waiting. What is the frequency of that graph? If you don't understand, quickly tell me, I can explain. But I expect that having been taught, you should be able to answer that question. Said 2 hertz. No. No. You have tried, but that is not. Any other person? Just one more person.
4.
4. Thank you. That is the answer. Now, what is frequency? We just said that frequency is number of cycles. When you say number of cycles, if you look at a sinusoidal graph, where that line starts from, when you go up and down and you're coming up again, when you get back to that same place, you have covered one cycle. So if you look at that, that is 1, 2, 3, and 4. What of the one below? What of the one below? What's the frequency? What's the frequency?
3.
No, it's 8. It's 8. It's not 3, it's 8. But what do you observe? You see that the other one is getting thinner, while the first one was wider. That same concept is very synonymous to the concept of compression and rarefaction that we said the other time. You know, one is compressed, one is spaced, right? So that is what we call frequency. And this application is seen in the voice of a baby crying and the voice of a grown-up man. I am sure you will understand and you'll agree with me that when a baby is crying, if that baby if that baby gets to that level, you will have to attend to that baby, because the pitch of that baby is so high that it may deafen your ear when a baby is crying. But if a man is crying, in fact, it will be kind of deep. You know, it's just like they are differentiating the way a man talks and the way a lady talks. It is only on rare cases that you see a girl that the voice will be thick like that of a male, right? So the voice of a female is usually soft and, you know, it's succulent, kind of attractive to the ear or something. But when a man talks, you just say, who is that one talking over there? So that is the difference between the pitch, right? So it's one of those things that we use to differentiate sound wave. Now, there are some situations that we now have an instrument producing the same pitch. How do we now differentiate them? Another way we can differentiate them is what we call quality or timbre. So what quality or timbre is just another characteristic that we use to distinguish a sound source or two sound sources with the same pitch, and it depends on the overtones present in the notes, and it also depends on the harmonics. By the time we are done with this, you will realize that there's a difference between overtones and harmonics, right? Harmonics is talking about how the multiples of the frequency, right? When we get there, you'll understand. But when we say overtones, you will ignore the fundamental frequency. The next one that follows, and as it keeps on progressing like that, is what we call overtones. So It depends on overtone. It also depends on the harmonics. WAEC usually alternates that question. So that's why we have to open up all possible options to you so that you know that when they twist it to another thing, they are still saying the same thing. You will understand perfectly. Then the last one is loudness or intensity. So loudness or intensity is just like you take your radio. You are listening to radio station and you increase it and it goes, when it goes up like that, you say you are increasing the loudness. That's just what that means. How it gets and how far it can get to the listener. So, and that is depending on the amplitude of the vibration. I hope we understand what we mean by the amplitude, the maximum vertical displacement of the wave particle. Going to the next slide because I'm sure time is fast spent. Let's take on echo. I think echo is the last topic, right? So echo is a sound heard after the reflection of sound wave from a plane surface. We said it the other time that an application of reflection is echo. Then we also have what we call reverberation. So reverberation is just when you have multiple echo. That's just what it means. The continuous occurrence of echo due to multiple reflection of the original sound. So you are in a studio, right? The studio have been designed so that it prevents echo. If you have ever been to all the radio stations, there was this year, I think that was 2 years ago or so, that I went to Ray Power to air a program. And when I was there, they had to tell me that I have to follow some precautions. You don't do this in the studio, you don't do that. I asked why, and they say it's to make sure that those things that they use to prevent echo are not affected. When you get to the studio, there is usually a padding. There's a padding that is placed on the walls of that studio center where the broadcaster is speaking, so that it will avoid echo, right? So when you have many echo like that, we call it reverberation. I don't know if some of you have experienced it also. If you have been to a hall that is wide, a bigger hall, and you are there, you say, oh, instead of you to hear, when you are there and you hear, oh, once after you have said it, that one is echo. But there are some, when you say, oh, you just say, oh, 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 oh. Even when you take your, when the DJ, they are testing their microphone, say, hello, hello. There is a way they tune it so that you'll be hearing that sound like 3, 4, 5 times. That kind is what we call reverberation. But if it is just repeated once, right, and probably after another seconds you hear another one, it's still within the ambient of what we call echo, right? So you should be able to distinguish between echo and reverberation. Then we go into the formula for the two of them. I think that's the last thing there before we talk about the application. So the formula just says the time is 2x over v. I think it's a straightforward thing. We know velocity is distance over time. But why is the distance this time around 2x? Because you are standing in front of a wall and you transmit sound wave. That sound wave covers a particular distance going to the wall, the distance x. Then that thing bounces back and come back to you by that same distance x. So x plus x, that's why it is 2x over v for the time. So if it is velocity, you have to find velocity is 2x over t. I think that is straightforward and simple. So we have an example here. The question says a person standing 99 meters from the foot of a tall cliff claps his hands and hears an echo 0.6 seconds later. Calculate the velocity of sound in air. So if you have to calculate the velocity of sound, it's very clear, straightforward. You have that, you have your answer. Velocity is 2x over t. You put the values and you have your answer. There are some other examples that I would want you to quickly write now. Please quickly write it and let me see who is going to give me an answer to that. Are we ready? Question says, a boy stands in front. If you are with me, just listen. I won't be too fast. A boy stands in front of a wall and fires a rifle. A boy stands in front of a wall and fires a rifle. And fires a rifle. Calculates and fires a rifle. Calculates the distance. Calculate the distance between the boy and the wall if an echo is heard 6 seconds later. Calculate the distance between the boy and the wall if an echo is heard 6 seconds later. Is heard 6 seconds later. Is heard 6 seconds later. Speed of sound in air equals 330 meter per second. Speed of sound in air equals 330 meter per second. Quickly solve that question, please. Yes. We have 2 minutes to finish this class. So please, let's round up. What's the answer to that question? I'm waiting. Quickly. Anybody? We are running out of time.
The question again.
Wow. You want me to repeat the question again? Okay. I said, a boy stands in front of a wall and fires a rifle. A boy stands in front of a wall. Okay, I'll type it on the chat page now. Should have gotten an answer now. Okay. Any answer? No response. Interesting. All right. So the answer to the question is, should I say it? Wow. It's a straightforward question. Anyways, the answer to the question is 990. 990 meters. 990 meters. So that is the answer to the question. So how it is 990, I expect that you should be able to do that. You are finding the distance, you have been given the time, you have been given the velocity. Now, apart from that, there are some other ways the question can come. But since you couldn't even give me a quick response on this one I have solved, and I don't have the solution to that question on this slide, I guess we should wait till the next class, so that by that next class I will have shown it on the slide. Because if I just say I should use my mouth to explain or write it on this page, I'm sure some of you will still have one or two challenge with that. So this is what we are going to call it a day. Okay, just quickly look at the application of echo. The application of echo, number one, use it to find the determination of speed of sound in air. We also use it as an echo sounder. Gas and oil exploration, determination of underwater objects, submarine. Clinical and industrial use of ultrasonic waves, determination of the depth of sea and location of shale or